All right, so here we are for section 2. It's going to be very similar to section 1, kind of like how the past few chapters have been. This is just about averages, about means. So same situations are going to apply where you have to check your conditions and such. Just remember it's going to be about averages, so we just have a little bit of slight change. So same exact learning targets, describing the shape, center, and spread, determining if conditions are met to do inference, then doing confidence intervals, calculating a test statistic and p-value, and then actually performing a significance test. So our beginning example for this is height, because height can be something that you average. So you have height of 10-year-old girls and height of 10-year-old boys. So notice the notation that they use to distinguish mu from boys and girls. We talked about with proportions, you have 1 and 2. Again, you can still use alphabet as well if it makes more sense. So we have a random sample of 12 girls and then 8 boys. So the sampling distribution of the difference between the means individually, these are their sampling distributions. Right? We know that the population is normal, so sampling distributions are normal. The mean of the sampling distribution is the same as just the parameter value. And then to calculate the standard deviation or the variability, you take the standard deviation of the parameter and divide by the square root of the sample size. And then, of course, your 10% rule must be valid in order to calculate that standard deviation. So here is a dot plot of the difference between the two sampling distributions. And remember, if we just take the sample heights and subtract them, we're just getting some random variable, some random number that's actually in the dot plot. The actual center of this dot plot is the difference of the parameter values. So you take those population values that you're given, and that is then the center of your graph. So standard deviation, we're combining two random variables. So again, we have to go along with adding their variance. Remember, variance is the standard deviation squared. So then we end up having to take the square root. Same thing as before, but our formula is slightly different because we're dealing with averages and not proportions. So overall, here's the breakdown of those different parts, the shape, center, and the spread that we talked about. So here's just an example in which we can go through each of those parts. What is the shape, what is the mean, and what is the standard deviation, and then interpret it as well. So we have fast food restaurant uses an automated filling machine to pour its soft drinks. The machine has different settings for small, medium, and large drink cups. According to the machine's manufacturer, when the large setting is chosen, the amount of liquid dispensed, noted by L, is a normal distribution with a mean of 27 ounces and a standard deviation of 0.8. When a medium setting is chosen, it dispenses on a normal distribution with 17 ounces and a standard deviation of 0.5. So to test the manufacturer's claim, the restaurant manager measures the amount of liquid in 20 cups using the large setting, 25 using the medium setting. So what's the shape and why? What's the mean? And what's the standard deviation? So it's normal because both population distributions are normal. There's no added work for that. The center, you take the difference of their parameter values, 27 and 17, so that gives us 10 ounces. And then our standard deviation, remember, we're going to add the variances. So we take the 0.8 squared and the 0.5 squared and divide by their respective standard deviations, their respective sample sizes. All right, and so the value is 0.2, so what does that mean? The difference, large cup minus medium cup, in the sample mean amounts of liquid typically varies by about 0.2 ounces from the true difference in mean of 10 ounces. All right, so confidence intervals. you have your same conditions as you had before, right? Random, 10%, and large counts. Random and 10% are the same as they are for, random is the same as proportions. 10% is your sample size, of course, same as proportions. Large counts is different. With proportions, you had to check that n times p and n times 1 minus p, all of those were greater than 10. But remember, with averages, you're looking at whether the population is normal, your sample size is greater than or equal to 30, or if you're given the data, then that data creates a normal distribution, or at least one that is not crazily skewed or has outliers. So here's our example. A college student wants to compare the cost of 1 and 2 bedroom apartments near campus. So she collects some data on a monthly rent of 10 apartments of each type. So 10 that have 1 bedroom and 10 that have 2 bedrooms. So mu1 is going to be the true mean monthly rent for 1 bedroom apartments, whereas mu2 is going to be 2 bedroom apartments. And so now we need to check that the conditions for finding the difference are met. So, random, they are independent samples of 10 one-bedroom apartments and 10 two-bedroom apartments. 10%, we pretty much assume that 10 one-bedroom apartments and 10 two-bedroom apartments is definitely less than 10% of all the apartments that are available 1 and 2 bedroom. Normal and large sample. So here's a situation where we don't know about the population distribution and our sample size is less than 30, so you have to provide a sketch of the data. So here we have a dot plot. Now you have 2 samples, so it's 2 that you're having to check. So we've provided a graph for each. If one of your samples is greater than 30, then you're only providing a graph sketch for one of the samples. All depends on the situation that you have. So we see that both of these are approximately normal, not like ridiculously strong with skewedness, but there are no outliers. And if you're not sure if there's an outlier, remember you can change a dot plot to a box plot on your calculator. And if you use a box plot, when it's graphed, if there's an outlier, there'll be a star or an asterisk, and that tells you there's an outlier. If there are none of those asterisks outside of your box, then there are no outliers. All right, so your confidence interval, the actual formula, same as before, right? You have the first line on your formula sheet, but you need to think of it in terms of all the other pieces, right? So you take the difference of the statistics. Your critical value is based on the confidence level. And then your standard deviation, well, that's going to change depending on the information you're given. If you know the parameter standard deviations, then you're using sigma. But we usually don't have that. That hardly ever happens. So we have the time where you have the sample standard deviations, and this is when you have S. This is when you're going to be using T star. T is what your critical value is based on. So we have to use our degrees of freedom. So altogether, this is the formula you need, and this is called a 2-sample T interval for the difference between 2 means. So again, if you're using a calculator, you have to provide the name of the test. If you're showing your work, then it's obvious through your work what you're doing. Now, your degrees of freedom, we have 2 samples going on. So one is you can use your calculator to do the work, and it's going to give you the actual value. Or what you can do, option 2, is your degrees of freedom is the smaller of the 2. So you take each of the sample sizes and subtract 1. Whichever one is smaller, that's the degrees of freedom you use. So of course, whichever sample size is smaller, that's the one you're going to use anyways. Now, if you're going between calculator and by hand on these problems for your homework, there is a huge difference in the degrees of freedom you get on the chart, that you get from your sample size versus what you get on the calculator. One person going by hand may get 24, but on the calculator, it's like 27.983. There's a whole algorithm in your calculator. So don't think you're wrong, it's just your calculator can be more exact. All right, so here we have the Wade Tract Preserve in Georgia is an old growth forest of longleaf pines that has survived in a relatively undisturbed state in a relatively undisturbed state for hundreds of years. One question of interest to foresters who study the area is, how do the sizes of longleaf pine trees in the northern and southern halves of the forest compare? We're comparing north and south. Those are our two groups. To find out, they take random samples of 30 from each half, and they measure the diameter in centimeters. Here's a summary. So they give us the summary of the information here, sample size, the mean, and the standard deviation. Now, our sample size is 30, so technically we can just say yes, it's normal, but they also provided a box plot here, so that's helpful. So, based on the graph and numerical summaries, write a few sentences comparing them. So remember, whenever you're comparing, you need to think about SOCs. When you say describe and compare, we need to look at all three of these. So we have shape, we have outliers, center, and spread. So talking about the northern being skewed right, and the southern is skewed left. There are no outliers. It appears that the southern half of the forest have larger diameters, right? They're centers. The mean and median for the southern sample is much larger than of the northern. Variability, there's more variability in the northern, right? That's definitely seen right here in the standard deviation. And also, if you think of range. Okay, now actually construct and interpret a 90% confidence interval for the difference. So, 90% confidence interval for the difference. Define what mu1 and mu2 are. Okay. Now, we're stating what the test is, or the confidence interval is, a two-sample t interval. Checking our conditions, random samples. We can assume that 30 from the north and 30 from the south are less than 10% of all of those trees in the forest, because it is a forest we're talking about. And both samples are 30, which qualifies to say that it's a normal distribution. Now we find the necessary information to then plug into the formula or use your calculator. Right, so we have our statistics, we have the standard deviation of the samples, and we have the sample size. So we can substitute all of that into our formula, or we can go into our calculator and we get our confidence interval. So notice right here, degrees of freedom from the calculator, 55.728. If we're doing degrees of freedom by hand, it would have been 30 minus 1. We would have had 29. These do not compare whatsoever, okay? So your calculator interval and the interval by hand are going to be different, and it is okay. As long as your work is consistent, the reader can see, oh, she's done all of her work by hand, this is the interval she should get. Oh, she's done the entire thing on her calculator, this is the interval you're supposed to get. So as long as you don't mix them up in the middle of the problem, all will be fine. All right, so here we go again. If you do it by hand, degrees of freedom are 29. So here's our critical value. And so here is our interval. So then we make our concluding statement. We are 90% confident that the interval from 3.9362 to 17.724 centimeters captures the difference in the true mean DBH of all southern trees and the true mean DBH of all the northern trees. If you're in your calculator, remember it's a two-sample t interval. You'll substitute all of your information in there, and then it'll give you your interval. Now, when we're doing things with averages, we don't do anything with pooled like we did with proportions, so don't worry about that. No pooled for means, for averages. Okay, the other thing that could happen is you have data. So if we have our data like the soda drinks from the restaurant or whatnot, we were given the ounces, we weren't given the summary statistics. What you would have to do is go into your calculator and go into your Excel spreadsheet, and you would have to put in the large versus the medium, and you would have to put in all of that data, then go to a calculator page and do your two sample t interval and choose statistics, data. Choose data, and then it's going to ask you what spreadsheet is it at and things like that. So, The formula for a two-sample t-interval often leads to calculation errors by students. Also, the interval produced by technology is narrower. Something to remember here. The interval produced by technology is narrower, but that's because the degrees of freedom situation. Okay? So, if you're using your calculator, be sure that you write down the name of the test, the interval that you get from your calculator, and the degrees of freedom. The degrees of freedom is going to be an obvious key as to which way you did your problem. Okay, so now let's look at hypothesis testing for the difference of means. Very similar situation. We're looking at where the difference is 0, right? The claim is that the new versus the old, or medication 1 versus medication 2, there is no difference between them. And we want to show that there actually is, or hope to show. So the way that you write your hypotheses is the same way, just obviously with mu instead of p. Your same conditions as with confidence intervals. So we're just going to do setting the hypotheses here, not the conditions. So, has the mean number of hours Americans work in a week changed? One of the questions on the General Social Survey asked respondents how many hours they work each week. Responses from random samples of employed Americans were recorded for 1975 to 2014. Here they are summarized. So, do these data give convincing evidence at the alpha is 0.05 significance level of a difference in the true mean number of work hours per week for Americans in 1975 and 2014? So our hypotheses for this, notice here that they have the subscript is the year that they're looking at. So instead of saying mu1 and mu2, they said mu 2014, mu 1975. So right here, mu1, mu2, they should really say mu 1975 and mu 2014. Even though it's obvious by putting the year there what that mu is supposed to stand for, you still need to define the parameter. I would hate for you not to define what they are and lose credit for something so silly. All right, so to actually carry out a significance test, you have your formula at the top of your formula sheet, but you need to think of it again in terms of all of the information. All the conditions are exactly the same, degrees of freedom are the same, just as you were doing with confidence intervals. All right, so let's go straight to a full-on, significance test. So back to that example of the working hours, explain why the sample result gives some evidence for the alternative, calculate the standardized test statistic and p-value, and then what's our conclusion? So the difference between the two, if you look at their averages, says that there is a difference, right? Those numbers are not the same. So it gives evidence that the difference between them is not 0. Then, filling in our formula for our test statistic, we get t is 4.88. So you can use your calculator, get a p-value using degrees of freedom of 1,660.58. You get a p-value of essentially 0. But again, it's a two-sided test because it said not equal. So we're going to multiply it by 2, 0.001. Okay. This is from using your table. All right, so because the p-value is less than alpha, we reject the null. There is convincing evidence there is that of a difference between the two. So, putting it all together, does increasing the amount of calcium in our diet reduce blood pressure? Examination of a large sample of people revealed a relationship between calcium intake and blood pressure. Such observational studies do not establish causation. Researchers therefore designed a randomized comparative experiment. The subjects were 21 healthy men who volunteered to take part in the experiment. They were randomly assigned to two groups. 10 who received calcium supplement for 12 weeks, with a control group of 11 who received a placebo. The experiment was double-blind. Remember, double-blind means the person handing off the medication to the participant does not know what they're giving, and then also the person who's getting or receiving the medication also is not aware of what they're receiving. The response variable is the decrease in the blood pressure for the subject after 12 weeks. So what they did is they took their blood pressure before they started the treatment, and then 12 weeks when they were done, they took their blood pressure again, and they subtracted to figure out what the difference was. So negatives mean that the blood pressure actually went up, whereas positives mean the blood pressure went down. So, do the data provide convincing evidence that a calcium supplement reduces blood pressure more than a placebo on average for subjects like the ones in the study? So, we have mu C, those taking the calcium, and mu P, the placebo, is 0 versus greater than 0. Again, if you see a positive value, that means their blood pressure was higher in the beginning, and then we subtracted a lower blood pressure. So we're looking for positive values. So it's a 2-sample t-test. It's random subjects assigned, or volunteer subjects that were randomly assigned to their treatments. The sample sizes are small, but here we have our dot plots that show no strong skewness or any outliers. So now we're calculating everything. We have our statistics, we have our standard deviations from our samples, and we have our sample sizes. Plugging everything into the formula, T is 1.604. So on the calculator, you get a p-value of 0.0644, degrees of freedom 15.59, or if you're doing it by hand, 10 was our smaller sample, 10 minus 1 is 9, so degrees of freedom are 9. Looking at our table, we get a p-value that's between 0.05 and 0.1, which obviously 0.06 does fall in that interval. So because the p-value of 0.0644, or you can refer to your interval of 0.05 and 0.1 is greater than alpha, we fail to reject the null hypothesis. The experiment does not provide convincing evidence that the true mean decrease in systolic blood pressure is higher for men like those who take calcium than those who take a placebo. So, interpreting our p-value. Assuming that the null hypothesis is true, there is a 0.0644 probability of getting a difference in mean blood pressure reduction for the two groups of 5.273 or greater just by chance involved in the random assignment. Again, you can still get all that information straight from your calculator. So, again, make sure if you're using your calculator, you give the name of the test, the statistic, the p-value, and the degrees of freedom. And that's it for this section.